Before the review that we have at the end of every module, I want to give you a kind of overarching summary of where we have now gotten. Okay, so what we have found is that we should think about reality in the following way. So reality is nothing but a collection of events, right? So firecrackers explode, races begin, objects fall. They're a collection of events. Now, remember, what is an event? An event itself is nothing but something that takes place at one single location in space and at one single moment in time. And of course, that's why we like to talk about firecrackers exploding and guns firing, because it really intuitively gives you that sense of it happening at one moment in time. But think about reality as just a grand collection of events, which are things that take place at one particular position in space, one moment in time. So if you want to make a list, therefore, of what constitutes reality, well, we can make a little table, if you'd like. And why don't I make this sort of neat for us here? So let's imagine that I have a little chart like this. And let's say I've got, well, let me, while I'm at it, put this guy over here too. Extend this guy a little bit. So imagine, therefore, that I have event number one. It can be, say, a gun firing or a firecracker exploding, whatever. Some event number one, some event number two, some event number three. And in principle, I could list out all the events that constitute reality. It would be a pretty long list, but this is, in principle, how I could delineate what comprises reality. Now, when I look at these events from the perspective of two different observers, let's look at them from the perspective, say, of Team Platform and the perspective of Team Train. Team Train and Team Platform will all agree on the events themselves. Every observer agrees on the events. The only way that they differ is in where and when each of them says that the events take place. So Team Platform might say event number one took place at T1, X1, and say event number two, perhaps they say it takes place at T2, X2, and event number three, say at T3, X3, and we could keep on going if we wanted to. Team Train will assign its own space-time coordinates to those events. So Team Train might say that this event number one happens at T1 prime, X1 prime, T2 prime, X2 prime for event number two, and say T3 prime, X3 prime for event number three. They all agree on the events. They just don't agree on when and where those events take place. And what the Lorentz transformation gives us is a simple, comprehensive mathematical dictionary that allows us to translate from the space and time coordinates according to one observer to the space and time coordinates according to another observer. That's all that the Lorentz transformation is. So the result that we have found is that T prime is equal to gamma times t minus vx over c squared, and x prime is equal to gamma times x minus vt. So if you know the t and x coordinates for a given event, you can use this transformation to fill out this table, and vice versa, using the inverse Lorentz transformation that we wrote down, where interchange the primes and unprimes and change the sign of the velocity, because from Team Train's perspective, Team Platform is moving in the opposite direction. This is all that the Lorentz transformation is. And again, the physics behind this transformation is nothing but the ingredients that we have carefully, painstakingly derived, right? Time dilation, Lorentz contraction, and asynchronous clocks. So the second thing that I'd like to do in this little wrap-up of Lorentz transformation is just show you how to get Lorentz transformation and time dilation and asynchronous clocks from the Lorentz transformation itself. Since we use those ideas to get this result, we should be able to extract them back out, and it's straightforward to do that. Now, to do that, let me also bear in mind that I'm assuming, as we always do, that team platform and team train, that their origins, the space-time origins, agree, so that when t and x are both equal to 0, t prime and x prime are both equal to 0 too. And I mention that because really the right way of thinking about this Lorentz transformation is in terms of the coordinate differences. But when an event takes place at that space-time location, and you're looking at its coordinate distance from the origin, or more precise, I should say, the coordinate difference, not distance, coordinate difference from the origin, I would just be subtracting off 0 and 0, so don't bother writing it down. But the general result that we have seen, you will recall, is that I can write delta t prime is equal to gamma times delta t minus v delta x over c squared, where now I'm looking at the space and time coordinate differences between two events. It could be two of the events that I have on the board here. And delta x prime is equal to gamma times delta x minus v delta t. And for good measure, let me put down the inverse transformations just so that we have them on the board here. So delta t is equal to gamma times delta t prime plus v delta x prime over c squared. And delta x is equal to gamma times delta x prime plus v delta t prime. OK, good. That's worthy of a little box, just so that we have it right in front of us. OK. Good. Now, let's use this to just see where Lorentz contraction and time dilation and asynchronous clocks arise in this little formula. It will just take us a moment. So let's do number one. Let's look at time dilation. So the canonical situation is I am looking at a clock that's in motion, right? Now, if the clock is in motion, in its own frame of reference, which would be the prime frame of reference, delta x prime will be equal to 0. Now, if delta x prime is equal to 0, I can use this little equation over here and write delta t is equal to gamma times delta t prime. And notice that because delta x prime is equal to 0, this term over here drops away. And that's the result I have. And there you have it. That is time dilation. The amount of time between two events on my clock will be bigger than the amount of time in the moving clock by a factor of gamma. So manifestly, we have now extracted familiar time dilation from the Lorentz transformation. OK, let's move on and look at length contraction or Lorentz contraction. How do we pull that out? Well, it's as easy. So in the canonical example of Lorentz contraction, I'm looking at an object in motion. And what I do is I measure its front and its rear at the same moment in time, right? So that means the separation between those two measuring events, delta t is equal to 0. I measure the front and the rear at the same moment in time. Now, I also know in these canonical examples that delta x prime, the length of the object, according to those moving with it, is the rest length of the object, L naught. What do I measure using the Lorentz transformation for the length of the object itself? Well, which formula shall I use? Let's use formula number 2 over here, because delta t is equal to 0. That will make that a particularly nice formula. So we find delta x prime is equal to gamma times delta x. And I don't have to write anything else down, because again, come in over here, delta t is equal to 0. And now if I just solve for delta x, the length that I measure, I get delta x prime divided by gamma, which is equal to L naught divided by gamma. The length I measure is contracted by a factor of gamma. So there we have length contraction or Lorentz contraction, again, coming right out from the Lorentz transformation equations. And just for good measure, let's finish this up and talk about asynchronous clocks in the moving frame of reference. So how does this work? Well, again, canonical example. I'm looking at clocks in a moving frame of reference, and I look at two of those clocks at the same moment in time from my perspective, simultaneously from my perspective. So again, that means that delta t is equal to 0. That looks like a delta gamma. Sorry about that. Let me just clean that up a little bit for you. So delta t is equal to 0. That looks better. Now, with delta t equal to 0, let's use this third of the Lorentz transformation equations. So if you zoom in on here for a second, if delta t is equal to 0, I can take the gamma, immediately divide it through, and therefore just set delta t prime plus v delta x prime over c squared equal to 0. So let me just do that over here. So this tells me, therefore, that delta t prime plus v delta x prime over c squared is equal to 0. And therefore, I conclude that delta t prime is equal to minus v delta x prime divided by c squared. And you will recognize that as telling me that there is a difference in the readings of the clocks in the moving frame of reference that is given by the velocity of the frame of reference times the distance between the clocks as measured in that frame itself divided by c squared. And you will recall that is exactly the formula that we have derived earlier, that we have been using for the asynchronous nature of clocks in the moving frame of reference. So the bottom line is we now see how all those familiar features that we have derived over the course of the previous modules are completely embedded in these Lorentz transformation equations. You can pull them out by carefully applying these equations. And indeed, these equations are nothing but an encapsulation of those ideas. So when you look, for instance, at an equation like this, right? If you focus in here for just half a second, you see right away, in fact, let me use this one over here instead. You see right away that this term over here is nothing but the time dilation factor, and this term over here is nothing but the asynchronous clocks in the moving frame of reference. That's what that formula means. Every time you see that formula, I want you to think about these physical features. When you see that gamma, time dilation. You see this v delta x prime over c squared, just don't think of it as a formula. Think of what it means. This is the asynchronous nature of the clocks in the moving frame of reference. And similarly over here, in this formula, it's better actually to divide this through by gamma. In fact, let's use this one, the one that we used before. So if you think about this as delta x prime over gamma, that is Lorentz contraction. That's length contraction. And the remaining term over here, delta x minus v delta t, that's just the usual Galilean motion of one frame relative to another. So the reason I'm emphasizing this is I don't want you to look at these equations just as mathematical symbols. Every time you see them, think about the underlying physics that is embodied in those equations. Nothing but time dilation, Lorentz contraction, asynchronous clocks in a moving frame of reference. And collectively, it all is just, again, telling us reality, collection of events, different observers assign different space-time coordinates to those events. They all agree on the events. They don't agree on where the events happen or when they happen. And the Lorentz transformation equations give us the dictionary to go from one to another. That's what this is all about.